Hello, and welcome to my talk entitled A Journey Through Autonomy. For me, this journey began back in 2000s when I saw that computers and cameras were everywhere. So I thought this is a good time to start teaching computers how to understand our world. And to do that, I decided to enter the PhD program at Stanford. So I approached a very famous and well-respected Stanford robotics professor for some advice. To my great surprise, when I told him how excited I was about robotics, his response was extremely discouraging. He said, "Don't waste your time. Robotics is dead." And he explained that for decades, scientists have been trying to figure out how to bring robots out of labs and factories out into unstructured human environments. And it just wasn't working. And he didn't see that it would change anytime soon. I'm really glad that I didn't listen to his advice and instead found some other faculty at Stanford that were much more excited about the future of robotics. By 2007, I was at the DARPA Urban Challenge in Southern California. Together with my Stanford teammates, I was watching our Robert Jr. perform gracefully alongside other contestants. The robots were polite to each other and to human-driven vehicles. They followed all the rules of the road, and they ran many missions completely autonomously all around the small town. To many of us, this was the moment when we realized that autonomy has entered our world and that it was here to stay. Of course, we realized there was still much to be done to make the technology more robust and safe before it could be released to general public. But this event has spawned a lot of industry and academia efforts in order to make autonomy a reality. For example, Junior's technology and much of the Stanford team went on to Google and later Waymo to keep working on autonomy. What followed was a period of rapid development during which autonomy grew by leaps and bounds. And just earlier this month, Waymo announced that it is opening up its autonomous taxi rides to general public in Phoenix, Arizona. This is a huge milestone. It means we've made it. We've managed to bring autonomy to the general public. So this is a great honor for me to be giving a keynote for Iris Autonomy Track during this exciting moment in autonomous evolution. My sincere thanks to Paul and the rest of the Iris team for making it possible. In this talk, I want to tell you about my journey through these times, the technologies I have built, the teams I have met, and the insights I have gained. I will start with some abstract theoretical observations and then quickly move on to the more practical. The goal of autonomy is to build autonomous agents that operate safely and efficiently in our world. So far, the best autonomous agents in existence have been built by nature. So let's see how it did that. It started with neurons and connected them in more and more complex neural networks. At this point, the intellect was intuitive. But then, as it made the neural nets more and more and more complex, eventually a new type of intellect evolved, what we call abstract thinking. Of course, abstract thinking is responsible for much of humanity's progress in science and technology, and understandably, we wanted to extend it to make it even more powerful. So we built computers in order to augment our abstract thinking. And indeed, they're very good at performing complex computations very precisely, and at this task, they are far better than humans. However, we then decided that we want computers to operate autonomously in our world, to become autonomous agents. And something very interesting happened here. When we tried to release them into the world, they failed. They got overwhelmed by uncertainty and noise and hidden variables and unexpected objects jumping in the robot's path and so on. So this was exactly the failure that the Stanford professor was warning me about. So we had to go back to the drawing board and develop methods for handling uncertain, fuzzy information, which was sometimes faulty and sometimes insufficient. In our quest to develop methods that could cope with uncertainty, one type of methods became particularly popular. It is known as deep learning, and it is based on artificial neural networks. So it looks like we start with neural nets, found them insufficient, and developed abstract thinking. But then when we tried the abstract machines go out into the world, we were forced to add artificial neural nets. So this is very interesting. It is likely not a coincidence. And there are some reasons why both types of the intellect are required to make a capable agent. To understand that better, we need to consider the world in which these agents operate. As Mandelbrot wrote in his book, The Fractal Geometry of Nature, bark is not smooth, nor does lightning travel in a smooth line. He pointed out that while most scientists prefer to work with simple, smooth functions, which are easy to understand, almost all functions in the world are actually non-smooth. And in fact, the functions that describe nature are non-smooth. He developed the notion of fractals, which are infinitely complex functions. They're defined by infinite recursion, and no matter how far you zoom in, you see more and more and more complex structure. They're self-similar in the sense that at each zoom level, they display more and more and more complexity. So in essence, they are infinitely complex. So how do the two different types of intelligence perform given that the world is that complex? So first, the nature started with neural nets. They're essentially high-dimensional hill climbers, and because of that, they can be slow to train. Since the world is so complex, the best they can hope is to get to the bottom of a local minima, and so they have a tendency to get stuck. When abstract thinking evolved, it ended up giving us a huge boost. It provided a shortcut through this super complex space. Abstract thinking works by creating simple models, which are, of course, always wrong because a simple model cannot describe something that complex. And in fact, we call the difference between the model and the world noise. But these models are good enough to quickly provide accurate estimates at the scales that we need. On the other hand, when we try to put abstract thinking machines out there autonomously, they failed and they demonstrated the weakness of abstract thinking, which is that it is fragile. The simple models cannot keep up with the change when the world evolves in complex ways, with hidden variables, uncertainty, and noise thrown into the mix. As a result, the models become invalid and cannot recover. On the other hand, neural nets are very adaptive thanks to their hill climbing property, and they grab on to whatever pattern is actually there. So we can see how both types of intellect have very important roles to play. The neural nets provide robustness in the face of uncertainty and complexity, while the abstract intellect provides fast shortcuts and generalizations. And when combined, these two types of intellect produce highly capable agents. Shifting gears a little bit, in my thesis work, I have been focused on Bayesian methods for 3D perception. These are model-based methods that also are capable of accounting for uncertainty. And this is because they represent information in the form of probabilistic distributions called Bayesian beliefs. So for example, here is a belief for the problem of robot localization on a 2D map. As you can see, it is almost zero everywhere in the building, except in one place where there is a super skinny and tall peak around the real position of the robot. If we plot the same belief in log scale, then we can see the complex structure of this function. And no matter how much we zoom in, this complexity persists. So from 100 meters, we could zoom in to 10 meters and then down to 1 meter. And all throughout, we see that the complexity still remains. So that means that the belief is a statistical fractal, which is what makes it so difficult to estimate accurately. Now, The problem of localizing on a 2D map is a rather simple one, and that is still solvable using particle filters. But if you want to localize an object in 3D space, that takes 6 parameters, so you have to solve a 6-degree of freedom problem. And that is prohibitive for naive particle filter approaches. So instead, we developed a divide and conquer approach that solves the problem using broad particles at a very, very coarse resolution, rules out low probability regions, refocuses on high probability, zooms in, and keeps repeating the refinement process as many times as needed until the desired granularity is reached. The important thing is that throughout the scaling process, we maintain self-similarity, by which I mean that within each particle, we always subsample the same fixed number of smaller particles. And then if we zoom in on one of those, then we again subsample the same number of small particles. And again, this is important so that we always maintain a healthy density of particles representing the peak of the distribution. And this is what gives the method its robustness. We called this algorithm scaling series, and we compared it to state-of-the-art on a number of problems. Here is an example of 6DoF object localization. As you can see, the best advanced approach we were able to find was the annealed particle filter, which is this purple line here. And with respect to that, scaling series was able to gain about 2 orders of magnitude. And so this is the method that helped us in many applications to produce very accurate results in a very efficient manner. In 2015, I founded a 3D mapping startup called Eonite, and at first we focused on mapping out homes using commodity depth sensors. For trajectory estimation, we used the scaling series approach that I just described earlier, and it gave us much higher frame-to-frame accuracy than the state-of-the-art methods. So at the time, state-of-the-art for this sensor was around 1 centimeter frame-to-frame accuracy, whereas we got something on the order of 100 micron. And this high accuracy allowed us to map out fine details, such as, for example, this business card on the table, which is only about 200 micron thick. The high accuracy of the trajectory was actually extremely important for mapping out homes because we were able to map them out open loop, and our accuracy was sufficient to do so. Which meant to map it, we would simply walk through the home with the sensor, and in real time we were able to produce a full map. State-of-the-art approaches, on the other hand, had around 1 centimeter frame-to-frame error, which means that they had to rely on loop closures in order to straighten out the map. But in homes, this can be difficult to do, especially in between adjoining rooms. So you can imagine going from one room into another, and when you come to the wall separating the 2 rooms, you have nearly completed the loop, but you cannot close it because you cannot see through the wall. On the other hand, the wall itself is only a few centimeters thick, so even a few centimeter accumulated error in the trajectory will already break the wall, making the map unusable. For applications, we initially focused on AR and VR. For AR, we treated virtual characters as autonomous agents, and they had all the environmental awareness and planning expected of autonomous agents, which allowed them to behave much more naturally in homes, um, and feel like they were much more realistically part of the environment. For VR, we implemented highly accurate head tracking, which was done inside out, and so provided even higher angular accuracy than any of the outside in approaches. So as the AR and VR markets cooled, we pivoted into doing large scale maps using LiDARs, and we were lucky that um, the technology carried over from using depth cameras to LiDARs and from doing uh, indoor home maps to city scale maps. As before, we were getting very high level of detail in these maps, high localization accuracy to sub-centimeter, and of course, everything running in real time. The high level of detail in this case is particularly important because it allows us to capture small obstacles and changes in the road surface, such as small curbs, ramps onto the sidewalks and driveways, speed bumps, and any other irregularities which are important for an autonomous vehicle to know about, yet are rather difficult to capture using other means. Sub-centimeter localization accuracy helps when you want to get good ground truth for training your DNNs. So the pivot was highly successful, and in 2018 we were acquired by Mobileye. In addition to capturing the shape of the environment, we're also able to texture these surfaces with high-resolution textures, either using LiDAR intensity or RGB camera data. And here are the mapping stats for reference. I will only point out that the Metro New York City with area over 300 square miles fits into 600 gigabytes. So can easily fit on a hard drive, and therefore these maps provide a very practical solution. I first got to work on this problem back in 2007, and back then, most vehicle tracking approaches were cluster-based, meaning that they would take the LiDAR scan, divide it into clusters based on range discontinuities, and then try to reason how the clusters in one frame match up to clusters in the other. We proposed the use of a geometric model, although a very simple one is just a box, but it already helps greatly with association tasks. For example, a small obstacle can split the vehicle scan into multiple clusters, and now the algorithm somehow has to figure out that these two clusters go together. On the other hand, with the box model, it is much easier to make the association, and the small obstacle in the foreground doesn't really make that big of a difference. Another reason why shape estimation is important is in order to get a good estimate of the velocity of the object you're tracking. So this is true for both stationary objects and moving objects. Here I will show this on the example of a stationary bus because it is the easiest to see. So let's say we have a parked bus and we're passing behind it. In the first frame, we see a single cluster from the back of the bus, and the center is right here. So the algorithm decides that there is an object located at this point. In the next frame, we move forward and we see both the back and the side of the bus. It's a much bigger cluster, and the center has now moved up here. So to the algorithm, it looks as if this object moved from here to here. So this is a phantom motion, which is simply due to the fact that we're observing a different part of the shape and not due to the motion of the object itself. With shape estimation, however, it is not a problem. So at first, when we just observe the back of the bus, we estimate its width, and we decide that it is probably the length of an average car. When we move forward, we now see the back and the side. We can tell that this object did not move because the back did not move, but that our estimate of the length was much too short, and so we simply update our belief about the shape. So if you're having trouble detecting when vehicles are stopped or moving near a stop sign, then estimating the geometric shape of vehicles may be a good idea. Since 2008, we've made a number of improvements. So back then we started with a simple box model. It has later been extended to circles and ovals to track pedestrians and bicyclists. However, by now we extended that to complete 3D mesh models. So this could be built using the mapping techniques that we discussed earlier. To within about 30 meters, it works well to estimate the shape of the objects as we're passing them. But when these objects are further than 30 meters, that tends to be not enough information to accurately track their sixth-of pose. So at that point, it makes more sense to switch to a 2D representation. So simply project everything down to 2D um, and run an equivalent of the mapping into D, and instead of a triangular mesh, produce a polyline representing the shape in 2D. So either the 2D or the 3D works very well. This approach is fast and lightweight, and it can represent an arbitrary shape. It performs better than the box model because it fits the shape much better, and therefore tracking becomes a lot easier. We also made improvements in obstacle versus ground segmentation. Back in 2008, we did this for each scan separately, and this worked well for segmenting out large obstacles such as vehicles, pedestrians, and buildings. However, it completely failed for small obstacles such as curbs and speed bumps. Moreover, it did not provide any information on local slope or roughness of the ground surface. By now, we are utilizing our real-time mapping approach to produce what we call a drivability map, which not only gives you the driving surface, but for each surface point, it also gives you the local slope of the surface. For example, this map here has been colored using the local slope, where green means 0 degrees, perfectly flat, and the bright red means 90 degrees, in other words, perfectly vertical. We also realized that obstacles or not is not always a binary decision. For example, on this map, there are these thin curbs that you are expected to avoid while driving. On the other hand, if you want to park, then you're expected to drive up onto these curbs to park. Speed bumps are another good example where you are expected to be able to drive over them, but at the same time, you want to know where they are so that you can adjust your velocity appropriately. So this method works very well for both large and small obstacles. It is widely recognized in the industry that safety is a critical challenge for autonomy. In fact, in this year alone, a number of safety efforts are underway, ranging from IEEE working groups to ISO standards. All of these efforts address different aspects of safety. However, none of them are on safety of perception. And if you're like me and think this is important, then let me know and let's do something about that. So how can we evaluate perception safety? Let's look at some recent results from a well-respected team associated with Uber. What we see here is a precision recall curve showing the safety numbers of their approach. The safety is lowest in low left corner and highest in upper right corner. So when I saw these results, I thought that something wasn't quite right. For one thing, none of these results actually reached 90% of safety. And how could you possibly drive if you couldn't see every ninth car around you? Moreover, when I plotted my own results from back in 2008, they ended up all the way up in the top right corner. So clearly something here is wrong. And I suspect that I know what the issue actually is. The issue here is how these results are scored. So traditionally, when solving an object detection problem, then all objects in the scene would be scored. However, from the perspective of the application, where only a very small number of these objects actually matter, namely those vehicles that are right around our ego vehicle. In order for the results to be meaningful, it is very important to score only the things that actually matter. Otherwise, an algorithm that does better on something that doesn't matter may end up scoring higher, and we certainly wouldn't want that. So in other words, we only want to score critical errors, which are errors that directly impact decision making. In order to define and score these errors, we would, of course, need to be aware of the decision-making policy. Luckily, there is an IEEE working group now, which is working on that, and we could simply use the recommended policy as a guide to implementing the scoring. So with this scoring in place, we would get results that are much more meaningful. But how could we actually make existing perception methods safer? Well, there are some teams that haven't given too much thought to safety. When I spoke to Shai and Amnon at Mobileye, it was clear that they really had it thought through. In fact, they have a paper published on the subject on their website. And if you haven't read it, I recommend that you do. So the idea is to implement the parallel perception stacks. Redundancy is often the solution that brings in safety, except in this case, I would replace the word redundant with the word diverse, as that better conveys the meaning. Think about it this way. What did you do the last time you were solving some important problem and you wanted to make sure that your solution was correct? You probably asked your friends or colleagues to double check the results for you. And parallel stacks, in effect, are doing that. They are double checking each other's results. Of course, in order for that to work, these stacks have to be working independently of each other, so there is no cheating. Once multiple stacks provide the results can be combined via union or voting and then shipped to the planner. So to what degree could multiple stacks really increase the safety? So on this plot, I'm showing single stack safety horizontally and resulting multi-stack safety vertically. And I have curves plotted here for 1, 2, 3, and 5 stacks respectively. So you can clearly see that more stacks makes the safety higher. And you can also see that safety gain increases with the safety of the original stack. Since we want to make autonomy safer than human driving, it is important to figure out where that fits in a scheme of things. It turns out that humans are quite safe drivers. And then if we want to improve on that safety, let's say eliminate 99.9% of all driving related fatalities, then we would need to set the goal several orders of magnitude higher. That would mean we would need to build a stack with 11 nines, which is very hard to do and even harder to test because the test set would have to have several orders of magnitude more data in order for the test results to be statistically significant. And so by my computation, that comes out to be a fleet of 100,000 vehicles collecting data for about a year. So that's quite prohibitive. But the good news is that if we go with multi-stack solution, then with a safety of 3 or 4 nines, which is quite attainable, we can actually hit the goal. And also this safety is much easier to test. Of course, multiple stack safety will only work if these stacks are independent of each other, or diverse as we've been calling them. So what are some of the sources of diversity? One source is a sensing modality. Most AV teams by now agree that both camera and LiDARs are needed for a safe autonomy solution. Another source is the approach. More and more teams are embracing the fact that they want both DNNs and model-based approaches to be part of their solution. And finally, the most difficult one is diversity on the level of the team. This would mean that if you're building multiple stacks internally, then the teams should not be comparing notes. And of course, the best way to ensure that a stack is independent would be to have it be built by an external team. Now, some companies are beginning to embrace this, but the reason that it's been difficult to adopt is that a lot of companies feel that high quality internal stacks are their source of competitive advantage. And that is still the case. I'm simply saying that the safest solutions will be those that combine high quality internal implementations with the top quality external stacks. That is the responsible way to get the best safety. With the start of the AI revolution, we have entered the age of innovation, or as some call it, the new gold rush, meaning that innovation is the gold, and I guess that makes scientists the gold ore. So this is great until you realize that gold always attracts prospectors, and they're not the nicest people in the world. To them, it doesn't matter whether something is unethical, immoral, or even illegal. If they can get away with it, then it's fair game. What's worse is that they see you as a commodity, something to be bought and sold. So here are a few pointers on how you could protect yourself. First, realize your strengths. If you're making a startup, realize that you're far better at bringing in deals than any biz dev or CEO that you could hire. Take it from me, the super introverted scientist. It turns out that investors, customers, and acquirers all want to see you and not your biz dev guy. To them, you're interesting because you are the inventor and you are the main asset. Moreover, you are far better at making higher quality connections. The best way to make sure that a deal goes through is to negotiate directly with the person who will be receiving your product or company on their side. Let's call them your champion. And then have your champion negotiate with other people on their side to make sure that they will accept all the terms of the deal. This way you avoid having to deal with their negotiators who primarily just want to try out all the tricks from their book to see how low you can go. Many times I've seen these people kill deals that were otherwise very good. Now, your weakness is that you are not as experienced as the prospectors. So if you're creating a startup or getting a job at a big tech firm, hire a good personal attorney. The IP laws that we have are from the industrial age and they're not well suited for the age of innovation. Some attorneys understand this and they will fight for you, the inventor. Some states are also improving the laws. For example, if you live in California, be sure to fill out your list of prior IP, putting down everything you worked on prior to joining the prospective company. This will protect you from being locked out of your field. And speaking of being locked out, If you're like me and you build a lot of IP on your own, then you need to decide whether you want to open source it or to patent it. Keep in mind that patenting means creating a weapon that later could be taken away and turned against you. On the other hand, if you publish or open source, that means that you will get the scientific credit, which will forever stay with you and can later turn into a higher position at a big tech firm. Finally, I'd like to wrap up the talk by reiterating a few key points. So first, we saw that due to complexity of the world, both abstract intelligence and neural net intelligence are needed in order to implement truly capable autonomous agents. Further, we saw that since the world is a statistical fractal, fractal-inspired algorithms such as scaling series, for example, can greatly boost robustness and reliability. We saw that city-scale 3D maps can give sub-centimeter localization accuracy that can be useful as ground truth, and they can also provide fine details of the road surface, such as speed bumps, curbs, and driveways. We also saw that modeling object shape greatly improves tracking performance and the estimation of the object velocity, which can be useful around stop signs, for example. We saw that safety of perception can be improved by using multiple diverse perception stacks, which in effect would be double checking each other. And diversity can come from varying sensor hardware, algorithms, or teams. I hope you enjoyed my talk. Thanks for watching, and I'm happy to take your questions and comments either in the chat or by email.